Dear all, welcome. The topic which we are going to discuss today is about relativistic and quantum electrodynamics. We will discuss a glimpse of four vectors, Lorentz transformation, D'Alembert operators, and based on that we are going to discuss a derivation to validate the invariance of Maxwell's equation under Lorentz transformation and in terms of four vectors. To begin with, let us start with the basic understanding. Let us consider a coordinate system which is at rest. Let us label it as S, placed at three coordinates x, y and z. Let us assume one more coordinate system S prime which moves with a velocity v along the x-axis. At this juncture, let us imagine one more imaginary point P from the system S and S prime, and for that the space and the time coordinates are given as x, y, z and time coordinate t for the system S. Similarly, x prime, y prime, z prime and time coordinates t prime for the system S prime. At this juncture, the Galilean transformation equation will be given as x prime is equal to x minus vt and y prime is equal to y, z prime is equal to z and t prime is equal to t. However, based on the experimental observation, it was concluded that the Galilean transformation equation failed to explain the laws of electrodynamics, and these equations requires substantial modifications. Lorentz, the scientist Lorentz, who introduced a new transformation for the equation, under which he considered that velocity of light in vacuum remains constant independent of the relative motions, and the Lorentz transformation equation accordingly are modified and represented as follows. The x prime is equal to x minus vt divided by the modified term, that is root of 1 minus v square by c square, and we will rewrite this equation in simplified form where beta will be labeled as v by c, and we rewrite it as x prime is equal to x minus vt divided by root of 1 minus beta square, where beta is equal to v by c. We will simplify further where we represent 1 by root of 1 minus beta square as gamma term, and we will rewrite as x prime is equal to gamma x minus vt, where the gamma is equal to 1 by root of 1 minus beta square. Let us label it as equation number A. Since the system moves along the x-axis, the term y-axis and z-axis remains unaltered. Hence, y prime is equal to y, z prime is equal to z. On the other hand, the term time coordinates t prime will be given as t minus vx by c square divided by root of 1 minus v square by c square. In similar to the previous step where we rewritten this term as in terms of beta and this term is in form of gamma, we will simplify this equation also, where t prime is equal to t minus vx by c square divided by 1 minus root of 1 minus beta square, and we will rewrite this term in terms of gamma, where t prime is equal to gamma into t minus vx by c square. Let us label these equations as A, B, C, D. So these equations represents the modified transformation equations introduced by the Lorentz for the system S which is at rest and S prime which is at motion. So the next topic will be based on the D'Alembert's operator. So if a wave is traveling in a space with a velocity v in a system S, the propagation equation will be given as dou square by dou x square plus dou square by dou y square plus dou square by dou z square, that is the position coordinate system, minus 1 by c square dou square by dou t square into psi is equal to 0. Let us label this equation as equation number x. So the terms within the parenthesis are defined as d'Alembert operator and labeled as box square. And we do have one more wave function, that is psi, in this equation. So the d'Alembert operator is defined as the sum of the second partial derivatives. We can see the second partial derivatives over here. So the d'Alembert operator is defined as the sum of second partial derivatives of a function with respect to each of its independent variables. This d'Alembert operator is particularly useful in analyzing the behavior of waves and signals in various physical systems such as vibrating strings, electromagnetic fields, and of course in quantum mechanics. So the next topic is about the four vectors. So the four vector theory was developed by Hermann Minkowski to reconcile the principle of special relativity with the classical physics. So in our lower class, in terms of classical physics, we represent the three components x, y, and z, which represent the spatial dimensions, whereas the four vectors here represents the four components with respect to the position and time, that is x, y, z, and ct, where c and t represents the velocity of light and time. The Lorentz transformation of space and time in terms of four vector form will be represented as a mu prime is equal to alpha mu v a v, where mu represents the four components, that is 1, 2, 3 and 4, and similarly the v represents the four components 1, 2, 3 and 4. Let us expand this equation number 1 as follows. So we can see here a1 prime, a2 prime, a3 prime, a4 prime. We can see the four components over here is equal to alpha mu v into, once again instead of v we substitute a1, a2, a3 and a4, where alpha mu v is represented by a 4 cross 4 matrix representation as displayed over here. Let us see how to understand this 4 cross 4 matrix representation. We do have the term gamma, like we have seen in the last slide. The gamma, this term gamma has its location in all the four corners. So we can see gamma, gamma, gamma and gamma, and I beta at the top right, minus I beta at the bottom left, and diagonally we have 1 and 1, and all the terms will be noted as 0. So this is the 4 cross 4 representation of alpha mu v. Now based on these understandings, our next task is to prove the invariance of Maxwell's field equation in terms of four vectors, of course by applying the Lorentz transformation. So let us start the derivation part. So let us start with the Maxwell's equation. Divergence of d vector is equal to rho, divergence of b vector is equal to 0, curl e vector is equal to dou b vector by dou t, curl h vector is equal to j vector plus dou d vector by dou t. So all these four equations collectively we can label it as equation number 1. Now in the other class we discussed the Maxwell's equation in terms of scalar and vector potentials. So vector form a vector and scalar pi potentials. We rewrite these equations in terms of scalar and vector potentials as follows. So del square pi plus dou by dou t del dot a vector is equal to minus rho by epsilon naught, and del square a vector, that is in terms of a vector, minus mu naught epsilon naught dou square a vector by dou t square minus del into del dot a vector plus mu naught epsilon naught dou pi by dou t is equal to minus mu naught j, where the middle term represents the Lorentz condition. If it is 0, the Lorentz condition is satisfied. So this two equations in terms of scalar and vector potentials we have discussed in the other class. Now these two equations, Maxwell's equations, we will rewrite these equations in terms of the box square, that is d'Alembert operator. So the first equation represents like box square and the scalar potential psi is equal to minus rho by epsilon naught. And the second equation, box square, the vector potential A vector is equal to minus mu naught J. Let us represent these two equations as equation number 3. And of course we do have the Lorentz condition over here, that is del dot A vector plus mu naught epsilon naught dou pi by dou t, that we can rewrite as divergence of A vector. So del dot A vector is divergence A vector plus 1 by c square, which is nothing but, hope you know that 1 by c square is equal to mu naught epsilon naught. 1 by c square dou pi by dou t is equal to 0. This will be the Lorentz condition for this equation as follows. Now the electromagnetic 4 potentials A mu and the current 4 potentials J mu will be given as A mu is equal to A comma I pi by C, and J mu, current 4 potential J mu, is equal to J comma I C P. Let us label this equation as equation number 5. Now we will apply the Lorentz transformation to this equation corresponding to the 4 potentials and current 4 potentials. So in the previous slide we have discussed the Lorentz transformation equation where A mu prime is equal to alpha mu v A v. This Lorentz transformation we are going to apply in the 4 potential equations. So we are going to apply this Lorentz transformation to equation number 5, and this equation 5 can be rewritten as A mu prime is equal to alpha mu v A v, and J mu prime is equal to alpha mu v J v. This will update the equation number as equation number 6, where alpha mu v is equal to the 4x4 representation matrix gamma 0 0 I beta gamma 0 1 0 0 0 0 1 0 minus I beta gamma 0 0 gamma. Now as we did in the previous session, let us expand this equation number 6 as follows. So where mu represents the vector component 1 2 3 4 and v represents the component 1 2 3 4. Let us start expanding the equation number 6. So we will read this first term, that A mu prime is equal to alpha mu v A v, as follows. So A1 prime, A2 prime, A3 prime and A4 prime, this left hand side will be equal to alpha mu v, that is 4x4 matrix representation, into AV. Instead of AV we have A1, A2, A3 and A4. Now let us take each terms outside. Let us do the multiplication process in the matrix representation. So A1 prime left hand side is equal to gamma into A1 plus 0 into A2 0 A3 plus I beta gamma A4. So ignoring these 0 terms, we do have A1 prime is equal to gamma A1 plus I beta gamma A4. And as we know that in the previous slide we represented beta as V by C. So we will write this equation, A1 prime is equal to gamma into A1 plus I V by C A4. Now we know that the term A4, we can read the term A4 by considering equation number 5. Like what we discussed in equation number 5, A mu is equal to A comma I pi by C, which means the fourth term, A4th term is I pi by C. So that fourth term will substitute in this equation A4. So what we get, A1 prime is equal to gamma A1 plus I V by C into the fourth term, A4th term, I pi by C. And as we know that I square is equal to minus 1, so we do have minus 1 symbol over here, which is represented as A1 prime is equal to gamma into A1 minus V pi by C square. Further, we will start expanding the A2 prime now. A2 prime is equal to 0 A1 1 A2, 0 A3, 0 A4. So ignoring all the 0 terms, we do have A2 prime is equal to A2. Similarly, the A3 prime term, A3 prime is equal to 0 A1, 0 A2, 1 A3, 0 A4. So we do have A3 prime is equal to A3, ignoring the 0 terms. The last term, A4 prime is equal to minus I beta gamma A1 plus 0 A2 plus 0 A3 plus gamma A4. So we'll read this equation as A4 prime is equal to gamma A4 minus I beta gamma A1, or let us take the common term outside, that is gamma into A4 minus I beta A1. So let us label these equations A1 prime, A2 prime, A3 prime, and A4 prime as equation number 6.1. So we have taken A mu prime and we have expanded the equations as 4 components, and we have finally achieved A1 prime, A2 prime, A3 prime, and A4 prime. Now the next task is we will take the J mu prime term and we will expand the matrix, and we have to find out J1 prime, J2 prime, J3 prime, and J4 prime in a similar fashion. So ignoring the repetition process, let us straight away go to the answer. So J mu prime is equal to alpha mu v Jv. We can read it thus equation as J1 prime is equal to gamma J1 minus rho v, J2 prime is equal to J2, J3 prime is equal to J3, J4 prime is equal to gamma J4 minus I beta J1. So if you compare this equation number 6.1 and 6.2, these equations correspond to the second, third, and fourth component looks exactly same. Second, third, and fourth components looks exactly similar. However, the first component, that is J1 prime and A1 prime, differs because in this J1 prime we have considered the term in equation number 5. Yeah, the J mu is equal to J comma ICP. So the J4, the fourth term here will be ICP. Similarly, in the other hand, the A4, the fourth term will be I pi by C. So this is what our consideration is. So only for that equation number there will be some small change between the relations. So accordingly, A1 prime will be given as gamma into A1 minus V psi by C square, and J1 prime is equal to gamma into J1 minus V rho. Now our next task is we have to update the Maxwell's equation in terms of 4 potentials. So we will take this Maxwell's equation what we discussed in the previous slide, equation number 3, that is del box square psi is equal to minus rho by epsilon naught, box square A vector is equal to minus mu naught J. We will add the term mu over here. So the updated 4 potentials and current 4 potential based Maxwell equations will be given as box square A mu is equal to minus mu naught J mu. This will be the Maxwell's equation for frame S, and the Lorentz condition will be dou A mu divided by dou X mu is equal to 0. Similarly, the Maxwell's equation for frame S prime will be given as, we need to add the prime symbols over here. So box prime square A mu prime is equal to minus mu naught J mu prime. So this will be the Maxwell's equation for frame S prime. Similarly, dou A mu prime divided by dou X mu prime is equal to 0. So that will be the Lorentz condition. Now our task is we need to validate the invariance of Maxwell's equation irrespective of the frame. So equation X, equation Y for frame S and S prime. So irrespective of the frames, in terms of 4 vectors, by applying this Lorentz transformation equations, our task is the Maxwell's equation remains same in both the frames. We need to prove that. So let's take the left hand side of the equation, box prime square A mu prime is equal to minus mu naught J mu prime So our task is, let us take the first term in the left hand side. So we take box prime square a1 prime, that is equal to box square a1 prime, because the d element operator of irrespective of the frame remains same. So box prime square is equal to box square. So our task is, we take this left hand side equation and we have to reach out minus mu naught j mu prime. So once we are done, then we can validate the Maxwell's field equation invariance term. Now let us substitute the term a1 prime from the previous equation. So over here, so we have obtained the a1 prime, a2 prime, a3 prime, a4 prime, and similarly j1 prime, j2 prime, j3 prime, and j4 prime. So in upcoming derivations, we are going to use this a1 prime term and j1 prime term. That is, a1 prime is equal to gamma into a1 minus v psi v pi by c square, and similarly j1 prime is equal to gamma into j1 minus v rho. These two equations we are going to use it up in the upcoming steps. So let us start analyzing the part. So box square a1 prime, substitute the term of a1 prime from the previous equation. So box square into gamma a1 minus v psi by c square, close the bracket, and bring this box term inside and bring the gamma term outside the bracket. So box square a1 minus v box square psi by c square into gamma, and once again this box square a1 and box square psi we have already framed up in equation number 3. So from equation number 3 we have box square a1 is equal to minus mu naught j1 minus box square psi will be given as minus rho by epsilon naught. So once again we will simplify this term, that is 1 by c square epsilon naught. We can rewrite that equation as mu naught. How? Because we know that c square is equal to 1 by mu naught epsilon naught, whereas mu naught is equal to 1 by c square epsilon naught. So take this 1 by c square epsilon naught and replace it with the term mu naught, and finally we have minus mu naught j1 plus mu naught v rho, close the bracket, gamma. So minus into minus, it's plus. So take the common term outside. We take mu naught into j1 minus v rho, close the bracket, gamma, and as usual we can say that j1 minus v rho by gamma, in the previous slide we have already derived the equation, that is j1 prime. So finally we have taken the left hand side, irrespective of the terms different frames, we have taken the left hand side, the d elements operator remains unaltered, and we have achieved the right hand side term mu naught j1 prime. Similarly we can able to prove that box prime square a2 prime is equal to mu naught j2 prime, box prime square a3 prime is equal to mu naught j3 prime, box prime square a4 prime is equal to mu naught j4 prime. So this left hand side we have taken this one and we have proved that the right hand side equations. Thus we can say that Maxwell's field equations remains unaltered, or the invariance of Maxwell's equation in terms of 4 vectors by applying the Lorentz transformation equation. Hope to see you all in another video. Have a nice day.